Welcome everyone to GIA Knowledge Sessions, a series of talks and seminars about gemology fueled by our decades of research. At GIA, we consider ourselves so fortunate to study and learn from gems, and it's our mission to share our discoveries and learnings. I'm excited to kick things off today. I'm Dr. Sally Magana, Senior Manager of Diamond Identification, and I'm joined by Dr. Ulrika Donens Johansson, Senior Manager of Diamond Research, and Dr. Mike Breeding, Senior Research Scientist. And they are going to tell us all about color change diamonds. Now, before we get started, just a bit of housekeeping. Everyone is automatically muted. If you have a question, please submit it using the question and answer feature you'll see at the bottom of your screen. Feel free to ask questions as we go. There will be a Q&A session at the end where Dr. Donens Johansson and Dr. Breeding will have the opportunity to answer some of your questions. We'll also send a recording of the session to you later today, and that message will also have a survey, so we'll love to hear your feedback. And with that, I'm going to pass you over to Ulrika.
Thank you very much, Sally. Good morning, good evening, and whatever time of the day it may be for you. Thank you for joining us today. As Sally introduced us, Mike and I will be speaking about color change diamonds. So these color change diamonds were first reported in 1866 by a Parisian diamond dealer, George Halphen. Now, for color change diamonds, they're defined as diamonds that can experience a temporary change in color due to changes in the environmental conditions. In 1943, the term chameleon diamond, the most famous group of these color change diamonds, was coined. And in this case, these stones, as those shown on the right, have this olivey green type color, which can change to a yellow hue upon heating. You can imagine that as a client, you might be potentially confused if you bought a green diamond or a yellow diamond and you found that it was a different color upon opening your box later on. Now, before we start thinking about what it is that causes these color changes, we need to take a step back and actually consider what it is that causes color in diamond in general. So diamond consists of a series of carbon atoms arranged in a tetrahedral arrangement, as shown here on the right. That is the crystalline structure of the material. The way that these carbon atoms interact with each other creates an electronic structure. Diamond is classified as a wide bandgap semiconductor. Other semiconductors that you might have heard of are silicon. Now, the fact that this bandgap is so large, 5.47 electron volts, means that if we convert it into wavelength, so the way that you describe light, we can see that that is a very, very wide range. In fact, it goes all the way from the ultraviolet into the infrared throughout the visible spectrum. This means that perfect diamond, if it has no defects or imperfections, would be fully transparent and colorless. However, although we like to think of diamond as being a perfect material, diamond is not perfect. Even those beautiful colorless stones that you might see in the trade, they are not perfect. In fact, every one of them contains minute lattice imperfections or defects. Now, defects is a term that sort of has negative connotations to some people, but the truth of the matter is these defects are what make diamonds unique. They're what give them personalities, and above all, they're what cause color. And as you know, many, many fancy colored diamonds are even more valuable than the perfect colorless stones. These defects can be separated into two groups: intrinsic defects that are either carbon-based defects or just small holes and vacancies. So these are effectively where you remove a single carbon atom and you leave a little hole, an atomic hole. That's known as a vacancy, signified by a V. You can have vacancy clusters, which are groups of these little vacancies, or you can have slip planes, slip and glide planes. And this is caused by sort of distortions to the lattice due to plastic deformation. Extrinsic defects are those that involve other elements incorporating into the diamond. Examples would include nitrogen, boron, or silicon-related defects in their complexes. So those can be multiple nitrogen type defects. They can involve vacancies as well. So there's a whole family of defects, both for nitrogen, silicon, and boron, based on these complexes. Some of these nitrogen-related features in particular are very famous. So for instance, you might have heard of A centers, which are nitrogen pairs, shown here. You might have heard of B centers, which are 4 nitrogen atoms surrounding a vacancy. You might have heard of C centers, which are isolated nitrogen. So just a single nitrogen atom substituting for the carbon. These 3 centers are the basis of diamond typing. So you might have heard of high purity type 2A diamonds. Those are the ones that don't show any nitrogen-related features in their infrared spectra. You might have heard of aggregated nitrogen defects. So those would be the A centers and B centers. So the presence and absence of defects in diamonds are the basis of the classification system of them. Also, there's a whole range of defects that haven't actually been structurally identified. We can detect their presence through spectroscopic means and their interaction with light, but we don't actually know what the atomic structure looks like. Now, these defects, the reason that they're important is that they can change the electronic characteristics of the material. So if you have your diamond conduction band and valence band separated by the band gap, if you remember, the perfect diamond had nothing in that clear white space in the middle. However, these defects are going to introduce little electronic states. And the key thing about that is that now suddenly these defects can absorb some of the light that is incident on the stone. This, in other words, means that not all light is transmitted through the diamond. This, if there's sufficient concentration of these defects, you will see color. Additionally, multiple charge states of defects can exist simultaneously. A defect can be considered neutral, negatively charged, or positively charged, depending on whether or not they have extra or fewer electrons. And this is a concept that we need to keep in mind when we start talking about color change diamonds, because that is the key feature that is causing this temporary color change. So we'll come back to that. An example of a defect that can exist in 2 different charge states simultaneously is a nitrogen vacancy defect. So we can see its little structure here on the right. So you have a nitrogen atom and a vacant lattice site. And it can exist in both the neutral, signified by 0, and the negative, signified by negative charge state. And in the spectrum in the bottom, this is an absorption spectrum. So we're looking at the way that light in the visible range is being transmitted through the stone and absorbed. And we can see these 2 little peaks. These are what's telling us that the nitrogen vacancy center is present. One of them at 575 is associated with a neutral charge state. Then it has further absorption band around here. And then the negative charge state absorbs primarily at 637 nanometers, but then it also has absorption in this region here. Now for this diamond, which you can see has a pale pink color, the presence of these 2 defects means that there's a lot of absorption in the blue, green, and yellow regions. And this means that most of the light that's being transmitted is in this red region, which provides this pink color. Now, keeping in mind all of these different defects, we can start considering color change diamonds. So here we have a plot that just shows some of the different wavelength ranges that these defects can absorb in. So you can see the nitrogen vacancy centers that we were just discussing here, but then we can see that there's a whole range of defects in diamond that can also absorb in different sections of the color spectrum. So some of these defects are known as donors. They can donate electrons, whereas others are known as acceptors. They can accept electrons. And then based on the complex interplay between these different defects in the diamond, an equilibrium concentration of those defects will be reached. Now, the interesting thing is that this electron can move around. So you can have charge transfer. In some diamonds, external changes in illumination or the temperature can temporarily change this charge balance. So you have this little picture here. In the corner, we have an electron, that is this big yellow ball, being thrown between these different kids. You can think of the same situation happening with these defects in the diamond. One of them has a donor, has an extra electron, and it decides, you know what, I'll pass it on to this other defect that will gladly accept it. The fact that you can change these, the charge state of these defects are generally classified according to whether they're photochromic or thermochromic. The photochromic defects are those that change based on where the charge can move around based on the incident light conditions. And the thermochromic ones are the ones that change based on heating. And we'll be discussing both these types of defects in the coming slides. Key thing is when this electron is moving around, it's going to change the balance of the relative concentrations of these different defects, and that is going to change the absorption of the spectrum. The key thing being that you're changing the color of the stone. And again, this is a reversible change by again, modifying the conditions of the stone. You can also revert it back to the stable color. Now, the most famous of this group of color change diamonds are chameleon diamonds, which Dr. Mike Breeding is going to be discussing in the next few slides.
Hi, everyone. It's a pleasure to talk to you today about these very ugly swamp water colored diamonds that you see on the left. When I came to GI about 17 years ago, there's something that really fascinated me, not because of their sort of muted greenish colors, but because of what happens when you heat them slightly. But you see what they do temporarily is change to this very beautiful orange yellow to yellow color. And this is where they get their name of chameleon diamonds, is because of this change. And as Ulrika mentioned, chameleons are really cool because they have this thermochromic effect, meaning this response to heat, this temporary color change, but they also have a photochromic effect. You can get a similar change if you take a chameleon diamond, then you put it in darkness for a period of time. And then when you take it out of darkness, the color will have changed in a very similar way. And I'll show you some examples. I always thought it was funny that the name chameleon, and I was surprised when I went on the web and tried to find some examples of actual chameleons, how easy it is to find green chameleons and yellow chameleons. And so I just showed this to emphasize why the name came about. It's a trade name. And even more fun is that photochromic effect that I mentioned. And I didn't even do this on purpose, but the green chameleon on the left is obviously a picture taken in normal lighting, and the yellow chameleon on the right is clearly taken in the darkness. So there's a little more to it even than you might think. So here's an example. This is the same diamond in all these images. In the upper left, you see the stable body color. In this case, it's sort of a gray yellowish green. The photochromic part of the effect, if you leave it in darkness for 7 days, you see it starting to get brownish yellow when it comes out. If you leave it in darkness for even longer, in this case 11 days, you see that it's starting to get even more orangey yellow. Well, the key bit of that is 7 days, 11 days, and I'll show you even more in a couple of slides. But the reason most people heat chameleons to see their effect is because the thermochromic effect is much faster. You can simply heat it, and in a matter of seconds, it'll go to an intense yellowish orange color, like you see here. So this is a little example of that. This is a little video. You see it's greenish stone. We put it over a simple alcohol burner. I'm sorry, the video is a little bit blurry, but I don't think you'll have any problem seeing the color change. This stone goes to a very nice orangey yellow, yellow-orange color after heating. Now, before I talk any more about this, I want to caution anyone to not heat diamonds. It's generally a bad thing, and it can permanently change the color. It's only these particular types of diamonds, these chameleon diamonds, that in which the color change is temporary. But if you don't know exactly how to identify it, or you're not sure, you're taking a big risk. Your diamond might go from being green to being permanently yellow. So to give you an idea and to reassure you that the color change is temporary, this is a chameleon diamond, the same one that was shown earlier. After heating with under an alcohol lamp, you see in the lower left array of images, the nice bright orange yellow color. And then over time, just a few minutes actually, in normal room light, it goes all the way back to a stable color. So it's really a fairly straightforward process. Some change back quicker than others. The same thing happens in darkness. But the problem with looking at a chameleon diamond in darkness is that some of them require a very long period of time in darkness to fully change color. This one we left in darkness for 48 days to get the color in the lower left. And in a matter of seconds to a minute, it had reverted back to its stable color. So this thermochromic and photochromic effect has similar results, but very different timescales involved, simply due to the amount of energy that's associated with the process. So You may be familiar with the articles that have been published in Gems and Gemology over the last couple of years about colored diamonds. And these are some diagrams taken from the one on green diamonds, just to kind of give you an idea of the array of chameleon diamonds that we've seen in the last decade or so at GIA. On the left, you can see the stable graded colors. Most of them are on the order of grayish yellow-green or grayish green-yellow. In fact, it's taking up 60% or so. And then another very common color is brownish greenish yellow. But one of the key bits to this is that in order for GI to call a diamond a chameleon diamond, we require that it had a green component to the color, be it a greenish or a green component to the hue. On the right, you can see the chameleon diamonds. They're not restricted to very tiny stones. Only about a third of the stones we saw were less than half a carat. And they're fairly equally distributed all the way up to 2 carats. And then even greater than 4 carats, there's a significant number of stones. So they come in a wide range of sizes. If we look at the spectroscopy to try to understand the atomic structure, we see that most chameleons, not all, but most, are type 1AA, meaning that they have nitrogen impurities in them. And those nitrogen impurities are aggregated into pairs of nitrogen atoms for the most part. We also see a very common theme in that they are all hydrogen rich. This peak at 3107 wave numbers is a hydrogen related defect in diamond. It's the most common one visible in FTIR absorption. If we examine the color though, we want to look at the visible absorption spectra, and Ulrika talked about this a little bit. And these types of diagrams, when the trace, the red line in this case, is high, that means those wavelengths of light are being absorbed more strongly. And when it's low, they're being more transmitted more. So that's the color that you see. Chameleons tend to have 3 major components in their visible absorption. An N3 absorption at 415 nanometers, which is 3 nitrogen atoms in a vacancy, which is very common in natural diamond. But more unique to chameleons is the combination of a 480 nanometer band, a broad band you can see here, and also another broad band that extends from about 700 out to about 900 nanometers. And this absorption is thought to be due to hydrogen. But the combination of the 480 band and this broad absorption from 750 to 800, where it's most prominent, gives a transmission window that gives a greenish color. And that'll be significant as I talk to you a little bit about the color change in a couple of slides. So another property of chameleon diamonds, which is not unique, but it certainly applies to all of them. It's not unique just to chameleon diamonds, is the fluorescence and the phosphorescence. That 480 nanometer band causes yellow fluorescence and yellow phosphorescence. Here you see 5 chameleon diamonds. Along the top row, you see their response to long wave ultraviolet light, so a handheld long wave UV lamp. And I don't know that you can see on there, but there's a very faint amount of phosphorescence as well on the second row. The third row shows their reaction to short wave ultraviolet light. You see it's also yellow to yellow orange, maybe a little bit greenish. But most importantly is that last row, and that's the short wave UV phosphorescence. This another requirement of calling a diamond a chameleon diamond, a GIA, is that we see this short wave UV phosphorescence. And if you're not familiar with fluorescence and phosphorescence, fluorescence is the color that is emitted from a stone while the light source, in this case ultraviolet light source, is on. And the phosphorescence is when you turn that light source off, if the color persists afterward for a period of time. And this shortwave UV phosphorescence, this yellow phosphorescence on the bottom row in chameleon diamonds, can sometimes be very long-lived and last for several seconds after the lamp's turned off. One of my favorite parts of chameleon diamonds is what happens when you look at them in deep UV, the fluorescence patterns there, or in a diamond view type instrument. That's what you see here. And in almost every chameleon diamond, you will see some combination that bears a resemblance to this, where you have a very heterogeneous look to them. In this case, you see there's a mostly inert area in the center with a lot of blue fluorescence in an octahedral pattern, little bits of octahedral growth delineated by the blue. But then you see a more irregular, more uniform greenish yellow fluorescence, in this case around the outside. These seem to indicate that chameleon diamonds consist of multiple stages of diamond growth that have different defects that are dominant. As I said, it's a pretty common feature, if not always present. It doesn't always look the same. You can see the three examples around the outside here, and then the one on the lower right is a little bit different. It's a banded version, but it still has this combination of the blue fluorescing areas and the greenish yellow fluorescing areas. And so we start to see this so consistently that you really think that this seems to be intrinsic to chameleon diamonds. So it must have something to do with why they actually are chameleon diamonds. If we look at rough chameleon diamonds, like the two you see here, we see that they're kind of massive. One thing you note is they tend not to produce nice octahedral crystal shapes. They tend to be very irregular. But if we look a little closer, you can see that many times they're quite color zoned. The one on the left here shows a very nice big chunk of near colorless diamond that's intergrown with sort of a grayish yellowish green, what we'd think of as a traditional chameleon diamond. But I think I can show you that it's the mixture of these heterogeneities that actually give rise to chameleons themselves. If we look at the long wave ultraviolet fluorescence of this stone on the left, I think it's pretty obvious that there's two different types of diamond here with very different concentrations of defects. Once again, we see bits of the blue fluorescence at the top, and we see the greenish yellow, the yellow fluorescence at the bottom. Remember that fluorescence that's excited by different wavelengths of light, long wave versus short wave versus diamond view or ultra short wave, tends to be slightly different in color because of the way defects respond differently to different energies. All right, so if we really want to learn more about something like a chameleon diamond, we really have to have something that we can work with. Or as you all know, I mean, in the diamond world and the gem lab, we can't go cutting up and destroying all the stones. So we use mostly non-destructive analysis. But in certain cases, we want to do more. So we purchased this diamond that you see at the top and on the left, the stable color, on the right, the heated color. And we polished it down to a set of parallel plates. So you can see at the bottom. Color looks a little different because the light's a little different, but it's the same stone. You see the color change from green to yellow. But now we have the ability to go through this stone and examine the interior directly without having to deal with the problems that faceting causes. For science, that is. For beauty, faceting is wonderful, but for science, it's a bit problematic. So here's that fabricated sample in the diamond view. You can see that it has the same sort of greenish yellow and blue fluorescence intergrown together. And on the right, you can see that when we look at the phosphorescence, that the phosphorescence is mainly confined to the areas that are greenish yellow fluorescing. So this tells us something as well. So that image is going to follow us, the fluorescence images, because we have this plate, we can now analyze, do spectroscopy in certain parts of the stone and know that we're just sampling those parts. So you'll see a red and a purple circle, and the color of the spectra that I'm going to show you in the next couple slides corresponds to that. The red circle or the red spectra are going through a blue fluorescing region, and the purple is going through a greenish yellow fluorescing. So this visible absorption spectrum, you can see it's pretty similar all the way across until you get out to the 650 to 800 range. And the part that's going through the blue fluorescing region of the diamond has a rise out there in absorption. And this rise is very common in diamonds that are rich in hydrogen. The region that's just fluorescing greenish yellow, however, doesn't seem to have that rise. So it suggests that the blue fluorescing regions perhaps are richer in hydrogen. Here's a photoluminescent spectrum where we shine a laser on the stone and measure the light that comes off. And the light comes out in the forms of both broad bands and peaks. But here we're looking at a peak at around 700 nanometers. You see that it's also concentrated. The 700 nanometer peak is larger in the region with the blue fluorescence than in the greenish yellow, with most of the other features being fairly similar. This is significant once again because this 700 nanometer feature is very common in hydrogen-rich diamonds. Whether it's associated with hydrogen or nickel has been debated in the literature, but it's always present in diamonds that have significant amounts of hydrogen in them. So I've shown you a couple of examples now from spectroscopy that seems to indicate that the blue fluorescing regions are different than the green fluorescing regions and that they contain more hydrogen. So that kind of leads me to a bit of a fun study, and that's kind of looking at, is this mixture of diamonds, this sort of morphological heterogeneity that we see, is that the reason that chameleons are what they are? Because from the absorption spectrum, I showed you that it requires both a 480 nanometer band and the 750 to 800 or so hydrogen related absorption in order to get the green color. So you have to have both, but clearly part of the diamond doesn't have both. So if we look in these diagrams, the purple trace, the purple spectrum is of a yellow-orange diamond that is purely colored by a 480 nanometer band. It does not have hydrogen. The red spectrum is a hydrogen diamond that doesn't have a 480 nanometer band. It tends to be grayish or greenish. The green spectrum in both plots is a chameleon diamond. And I think you can just look at this and see very clearly that if we add the two outside spectra together, we get something very close to the chameleon spectrum. And this seems to reinforce the idea that chameleon diamonds are made up of a combination of hydrogen-rich diamond and 480 nanometer sort of yellowish diamond. Same thing if you look in the spectrum on the right of the photoluminescence, you can see broad bands in the 480, a strong 700 in the hydrogen diamond, and the chameleon has both of those, along with some nickel-related absorptions as well. So it seems to be pretty good evidence that that's what we're looking at. So from all of this work, and not just from one diamond, mind you, this is seen repeatedly in many, many chameleon diamonds that are investigated, there seems to be a hydrogen-rich plus a yellow-orange component that combines to give you chameleon. Well, what does that have to do with the color change, you might ask? And that's the beauty of having a parallel polished plate that we can do experiments on. Next. And we've done just that. So these are all visible absorption spectra. So once again, the higher the line is, the more absorption. And the lower the line is, the more likely to have transmission. I know there's a lot of data here, and I'm sorry if it's a bit confusing, but the thing to remember is that the lines that are further up are at lower temperatures. The blue line at the top was taken at room temperature, that spectrum, and the red line at the very bottom was taken with the diamond heated to 450 degrees C. So these diamonds were analyzed while they were being heated, and so you can see the change. So I think you can very clearly see there's a 480 nanometer band, and there's a broad 750 to 800 nanometer band. Here, the spectrum extends further so you can see more of it. At room temperature, the lowest part of the spectrum is here between about 520 and 560 nanometers, which when you transmit light in that range, you get a greenish color, and that's what the stone looks like, and you can see from the photo. However, after we've heated it up to 450 degrees, notice that the broad band between 800 and 900 nanometers hasn't changed. It's always there. But what you see a difference is the 480 nanometer band. It hasn't disappeared, even though it appears to have a little. What's happened is it's broadened. It's gotten a lot wider with heat. And what that's done is it's shifted the transmission window. It's no longer in the green region. At 400 to 450 degrees C, it's shifted over here into the yellow region, or the orangey yellow region, at about 570 to 630. And that's why we see this orangey yellow color when the diamond is heated. So there have been other publications that have suggested that chameleons change color because their hydrogen band, or this 750 to 800 or 900 band, disappears. But our work has shown quite the opposite. That band seems to remain intact. And what happens is the 480 nanometer band expands with heating, or presumably with being left in the dark. Obviously, it's much more difficult to examine the photochromic aspects of this because it's difficult to collect the spectra in the dark, because as soon as you shine light on them to measure the spectrum, you change the color. But we have a way of testing this, and that's because there are natural diamonds that just have 480 nanometer bands. So I'm going to show you those in a couple, and I'm going to hopefully prove to you that This expansion of the 480 nanometer band is what's causing this change in color. In chameleons, it requires the hydrogen band to be present to get the initial green color, but it has nothing to do with the overall color change. So many of the most famous and most beautiful orange diamonds in the world are colored by this 480 nanometer band. It's an unusual defect because we don't really know what its structure is. It's been theoretically proposed to be oxygen atoms in the diamond lattice, but only through modeling has any of this been theorized. It's just not well known. It hasn't been proven or detected with any sort of instrument. But if we go to the next slide, we can see that when we take a diamond that's heated by the 480 band, the stable color seen on the left, we heat them and they become more orange, which is consistent with what we saw in chameleons. This seems to suggest that, yes, indeed, the 480 nanometer band is changing. We see it both in chameleons and in stones without all the features of a chameleon, as you see here. Take it a step further, and then we did the same heating experiments with one of those stones. Same type of visible absorption diagram. The plot at the top, the purplish one in this case, is at room temperature, and the sort of aqua blue color at the bottom is at 450 degrees C. I think you can see very clearly in the arrows indicating the shift in the transmission window. In this case, the transmission window was everything to the right of the 480 nanometer band. It's shifted to longer wavelengths and thus to more orangey colors. And so this expansion of the 480 nanometer band seems to be pretty reliably the cause of change of color here, and in conjunction with a hydrogen band, the change of color in chameleon diamonds from green to orangey yellow. So that's kind of hopefully a fun look at the science behind understanding why chameleons are what they are. And it may in fact be that they are what they are simply because they're a mixture of more than one thing, which to me is kind of cool and exciting, on top of the fact that we can change these defects in their absorption by heating or by keeping them in the dark. So with that, I'm going to pass it back to Ulrika, and she's going to talk to you about some other natural diamonds as well as some treated or laboratory grown diamonds that also have interesting color changes. Thanks.
So now we're going to move on to some other interesting natural diamonds that have color change phenomena. The next group that is also quite within the trade can be quite well known for changing color are natural pink diamonds. So here on the left, we can see two beautiful fancy vivid or fancy deep purplish pink diamonds. And the color of these diamonds arises due to the presence of absorption bands in the 550 and 390 nanometer region. Now, those particular defects, they haven't been identified, but we do know that they correlate with plastic deformation. Now, these defects, again, are photochromic. They are sensitive to lighting conditions. So if these stones were subjected to deep UV or shortwave UV, we will see that the change is quite dramatic. They go from these beautiful purplish pink colors to brownish colors, orangey pink colors. So effectively, the stones have been bleached. A lot of the pink has been removed. And there are several studies on these types of diamonds that have been published in the literature, as listed below. Now here we have the absorption spectra for one of these color change natural pink diamonds. In its stable state, it has a fancy intense pink grade. But then upon applying the UV light, we can see that the color changes to this fancy intense brownish yellow. So we can see the 550 band has decreased, as well as the 390 nanometer band has decreased. And this has changed the absorption spectrum in such a way that you've removed the pink and revealed the brown. Now, a lot of you might be alarmed. How do we bring it back? Well, if you illuminate the stone with approximately 30 minutes intense white light, so this would be, for instance, the white light coming from a fiber optic probe that you use when examining a diamond, or even the white light from a light well in a microscope. So something that's very, very intense and white. We're able to revert and restore the color back to its fancy intense pink. So it's reversible. the UV light bleaching efficiency is going to be higher for lower wavelengths. So if you were to look at this sample and illuminate it with a standard gem lamp, a combination gem lamp, with the long wave UV, you would see some change in the color. If you move on to the short wave UV, you're going to have a much more intense change in the color. And then finally, if you use the deep UV from, for instance, a Diamond View instrument, which has a wavelength less than 230 nanometers, you would find a very, very intense change in the color. So it would go from the two extremes. So these absorption bands, as I showed in the previous slide, are also thermochromic. So if you were to heat these diamonds, you can potentially intensify the pink color. Examples of that are people who are mounting their stones, and during the mounting process, the stones might get heated. That can modify the color temporarily. Also, some polishers will actually heat the stone intentionally with a polishing wheel, again, intensifying the color. If you were to keep the stone in the dark, this unstable color can be maintained for a very long time, of the order of 100 days. So that means that if you're working and grading a pink color diamond, you definitely have to make sure that you're grading the stable state. So at GIA, we have procedures for all of these color change diamonds to stabilize the color and ensure that the color that we have upon grading and upon the diamond leaving GIA is a stable color. So you can return to this equilibrium or stable color by illuminating the sample with either strong white light or even a LED that has a wavelength of about 465 nanometers. And that can be done in just a few minutes. On the other hand, if you were to leave it on the counter and expose it to ambient lighting conditions, it can take hours before it stabilizes. Another type of defect that is also associated with pink color is a nitrogen vacancy center. So famous nitrogen vacancy center pink natural diamonds are known as Golconda pinks. And they're extremely rare. They account for about 0.6% of natural pink hued diamonds. On the other hand, the nitrogen vacancy center is responsible for the pink color in the vast majority of treated natural or laboratory grown diamonds. Just like the 550 band diamonds, this MV pink diamonds are also photochromic. So in general, when you're considering pink diamonds, you should always be aware that some of them might be photochromic. So here we have 6 different diamonds, different growth methods, different treatment methods. We have the HPHD grown ones on the left, CVD grown ones, and treated naturals. So the HPHD and the CVD growth methods are the main synthesis methods for gem quality material. And all these diamonds have been treated in order to produce a large concentration of nitrogen vacancy centers. You can see that there's a range of hues, but they generally have an overall pink color to them. If you were to illuminate these samples again with UV light, we see the color shifting. So all of these intense pinkish, purplish type colors suddenly are shifting more towards a warmer hue, much more orangey in color. It's quite a dramatic effect. And some of these shifted colors are quite attractive, but in general, most people would be attracted to the stable state, so the nice pinkish purple color, or purplish pink color, sorry. So we look at the absorption spectrum for these diamonds. We can see that the stable state here, after illuminating it with white light, we have the presence of the nitrogen vacancy centers that we introduced previously today. So in the neutral charge state and the negative charge state. And we can see in this case that the absorption window is in the red, and then there's a little window in the purple as well. So that's what's giving you this sort of purplish pink hue. Now, if you illuminate the sample with the UV light, what happens is that one of the other defects that's present in the diamond, the isolated nitrogen center, the color change is occurring because of charge transfer processes that are occurring between the nitrogen vacancy center in the negative and the neutral charge state, and the isolated nitrogen center in the neutral and the positive charge state. The strong white light is able to restore the color in approximately 5 minutes, but this can take hours in ambient lighting. If kept in the dark, this unstable color can also be maintained for an extended period of time. Another set of diamonds that can show photochromic effects are these brown to pink as grown CVD diamonds. So they're grown using the chemical vapor deposition method. In the stable state, we can see that these stones have a brownish hint to them. After UV exposure, we can see that the brown color intensifies. And then if you heat these diamonds at temperatures of approximately 550 degrees Celsius, we can see that the color is bleached. Here we have the UV-Vis spectra for those stones again. And we can see that the main contribution to the absorption spectrum are the presence of the 270 nanometer band, which is associated with isolated nitrogen, the 360 nanometer band, and the 550 nanometer bands. Now, these two bands are currently not identified. So we do not know what the defect structure that creates them is. If you take your initial spectrum, so this is the green curve here, and illuminate it with UV light, we can see that there's an increase in the absorption of the 270 band, the 360 band, and the 515 band. Whereas if you heat the diamond, the intensity of those bands decrease. It is both photo and thermochromic. So again, we're able to maintain this UV or heated color states, so unstable states, for a long period of time if kept in the dark. However, once again, if you illuminate the samples with ambient lighting or strong white light, you're able to restore it back to the stable color. The stronger the white light, the more intense it is, the faster the color change will occur. Now, this is a feature that's primarily absorbed for as-grown CVD diamonds, as the HPHT treatment that is used to permanently decolorize CVD diamonds also destroys the defects responsible for the 360 and 515 nanometer bands. So since those bands have already been removed, you're not going to have the color change associated with them. We have noted that the magnitude of the color alteration depends on the concentration of the isolated nitrogen. So the higher the concentration of isolated nitrogen present in the stone, the more you're going to see this photochromic effect. And other defects have been associated with this feature as well. The defects involved include obviously the 360 and 515 nanometer bands, the isolated nitrogen in the neutral and positive charge states, and then another defect, which is a nitrogen vacancy hydrogen complex that again can exist in the neutral and the negative charge state. So it's by illuminating or heating the samples that you're able to move the charge from all these different defects and change the absorption spectrum and the color. Now, the final group of diamonds that we're going to look at are the high silicon doped CVD diamonds. Now, these are very, very rare. We have only seen a few handful of these over the years. And generally, when they're submitted to the lab, they have a fancy brownish pink, potentially a grayish type color to them. Not necessarily the most attractive of colors in the trade. However, if you illuminate these diamonds with UV light, the color improves dramatically. I mean, generally speaking, most people would say that these very beautiful fancy blue colors, fancy grayish blue colors, are going to be more appealing than the original browny pink or gray colors. However, this is again reversible. Illuminating the stone with white light will revert it back to its original stable state. So if we look at the absorption spectrum for these stones, in the stable state, so after subjecting them to white light, we can see that the spectrum is dominated by the presence of the silicon vacancy center at 737 and the isolated nitrogen at 270 nanometers. So here we have the defect structure for the silicon vacancy center. And silicon is something that can be introduced into CVD diamonds unintentionally due to the etching of the growth plasma of different silicon containing components in the system, in the reactor. So this could be, for instance, quartz windows. And this sort of introduces the silicon defects into the stone. Or alternatively, which is the likely case for all of these diamonds, they have been intentionally doped with silicon. So they have added silane to the growth gases or just a piece of silicon into the chamber during growth. Now, the reason behind the addition of silane is not really understood for these particular stones. As you saw, none of these diamonds in their stable state was particularly attractive. If we then illuminate the stones with UV light, you get this blue trace. And you'll see immediately that silicon vacancy center in the negative charge state decreases in intensity, and there's a rise in this region here. And this is going to result in transmission of light primarily in the blue. If we were to collect that UV-Vis spectrum cooled, so in this case, we've cooled it to 77 Kelvin liquid nitrogen temperature, which is about 196 negative degrees Celsius. It allows us to sort of sharpen these features. So it helps us identify which defects are present. So again, we can see the silicon vacancy center in the negative charge state. It's a little bit sharper. We can see a little bit more structure potentially associated with it. But then also we see that in the blue state, so after the UV light, a feature at 946 pops up. And this is the silicon vacancy center in the neutral charge state. We also see the rise here has a lot of little peaks. Now these are the photoconductivity spectrum of the silicon vacancy center, so in the neutral charge state. So all of these features, this absorption rise that is helping produce this blue color, is associated with the silicon vacancy in the neutral charge state. So the changes that we're observing are purely due to changes in the concentrations of the silicon vacancy neutral and silicon vacancy minus absorption features. UV illumination leads to an increase in the concentration of the neutral charge state and a decrease in that of the silicon vacancy minus. So that gives you the window that provides blue color. White light illumination returns it to the stable state. And if you were to heat these diamonds, they're thermochromic as well. In fact, heating the diamond will lead to a decrease in the silicon vacancy neutral center and a further increase in that of the negative charge state. So that could potentially turn the stone a little bit more browny pink or grayish pink than it was originally. It's certainly going to reduce the amount of blue in the diamond at least. Other defects that are involved in these diamonds include isolated nitrogen, again in the neutral and the positive charge state, the silicon vacancy defect 2-, the silicon vacancy nitrogen defect. So there's a lot of different nitrogen and silicon related defects that are present and contributing to this charge transfer process. These diamonds, if you kept them in the dark, they will slowly return to their stable state. But this can be the matter of hours or days. Now this feature is something that we see for both as grown and HPHT treated silicon doped CVD diamonds. So in summary, this slide here shows you all these different diamonds that we've discussed today. So everything ranging from the chameleon diamonds all the way down to the highly silicon doped CVD diamonds. And you can see the different states that they would be, the different colors they would have in their stable states, and then how they would change either by illumination with UV or potentially by heating the stones. And out of these, I'd say that the chameleon diamonds are attractive both in their stable and their unstable heated states. And potentially the highly silicon doped CVD diamonds are going to be more attractive after UV. However, the vast majority of these stones are actually going to look worse in their unstable state. So this is where it's really good to know that whenever you're looking at fancy colored diamonds that are within these color ranges, it's always worth illuminating them with very strong white light to ensure that you are looking at the true color of the stone. Now, the key thing that you have seen through all of these slides is that the color of these rare photochromic and thermochromic diamonds is only temporarily modified by these changes. These illumination changes might include using UV light, placing the stone in darkness, or even heating the stone. If you see such a change, don't be alarmed. It is reversible. Just use white light and you will be able to restore the color. The stronger the white light, the faster the restoration will occur. Now, this color change feature is actually considered to be very attractive for certain stones. For instance, chameleon diamonds. In fact, GIA reports it on their grading reports. The comment that would be included is the color of the stone changes temporarily when gently heated or when left in darkness for a period of time and is known in the trade as chameleon. As Mike mentioned before, be very certain that what you're looking at is a chameleon diamond before you attempt heating the stone. because there are other diamonds that if you were to heat them, you could permanently change their color. Also, it's worth considering that whenever you're buying or looking at a colored diamond, to check the grading report, because that will contain the stable color stated in the grading report. Alternatively, if you're looking at a stone that doesn't have a grading report, just make sure that you illuminate it with strong white light. And with that, I'm going to turn it over to Sally for any questions that you may have. Thank you very much for your attention.
Thank you, Ulrika. You and Mike had a lot of great information. We do have several questions from the audience, and so I'm going to first address some to Mike. And Mike, how hot do these diamonds need to get in order to change the color? And can they be changed by exposure to heat from daylight or body heat?
So from the experiments that we've done, it appears that the significant bit of color changing in a chameleon diamond starts somewhere between 150 and 200 degrees C. So that's pretty hot for normal conditions. So no, most likely not by body heat. Well, definitely not by body heat, most likely not by sunlight as well. To get them to change quickly, we put them in the alcohol lamp, which gets us a little bit hotter than that, but at least in practice, it seems to be about 200 seems to be a key point for the color change to start.
Okay. And are there any industrial applications for these chameleon diamonds?
Not that I'm aware of. I mean, they tend to be collector stones more than anything else. I mean, they're not particularly attractive, or at least most of them are not in their stable state. Occasionally you get a very nice green, but for the most part, I think they're just sort of novelties in the diamond gem world because of this color change and the fact that you can. There's also a photochromic effect. So even if you don't want to heat them, which, as we both mentioned, is a good idea not to do, you can put them in the dark and you can still see this effect after a little while.
Great. And how rare are chameleon diamonds compared to most other colored diamonds?
I don't have that data in front of me. I mean, amongst the colored diamonds, they only occupy a very small amount. I mean, of the percent range, and certainly not tens of percent. Among green diamonds, they're a little more common, but of course they can also fall into a sort of a yellow hue. I don't know how you worked on the articles with me. Do you remember? I don't remember the exact abundance.
I don't remember either. I think there was a couple of thousand from among that data set.
Yeah, so there's certainly something we see fairly regularly in the laboratory because they are popular in the trade. I think most people who send them in know that they have a chameleon diamond. So. Okay. And this is not related to that question, but I do want to emphasize again the same thing about heating diamonds. In fact, most green diamonds, if you heat them in an alcohol burner, you run the risk of permanently changing the color to yellow. So I strongly recommend against it unless you have a report from your diamond saying that it's a chameleon diamond. I recommend that you not go that route.
And speaking of which, we have a question asking, won't a direct fire burn the skin of a diamond?
If you immerse the diamond in the flame for too long, or the flame is too hot, certainly, well, you'll char the surface to start with. And if you do it too much in an oxygen atmosphere, obviously you can ultimately destroy your diamond altogether. So there's many risks associated with heating diamonds, and I know that when I showed that video, it's kind of a bit of a risky thing, but it can be done as long as it's done carefully. So. Okay. And you know what type of diamond you have.
Right. I'm going to ask Ulrika a couple of questions. What are the specific atomic defects that cause pink to purple color in diamonds?
So for pink diamonds, about 99% of pink diamonds are going to be colored by the 550 band. So these are defects that we don't know what the atomic structure is, but they have to do with a plastic deformation of the stone. So effectively, the stone has had shear forces, stress and strain when it was deep inside the earth. The alternative pink color comes from the nitrogen vacancy center. That accounts for approximately 0.6% of natural diamonds, extremely, extremely rare. And usually those diamonds, although pink, it's a very pale color. Regarding other pink and purple colors, I think Sally, you might be able to contribute a little bit more on that.
Okay. I think you answered the question very well, so I'll just move on to some of the other questions.
Okay.
I think just to a two-part question. One is, do all of these diamonds, such as the natural pink diamonds, will they all eventually revert to their stable colors? And then secondly, does GIA perform strong light illumination to check if a pink diamond is in its stable color state when it does the color grading? If you could perhaps reiterate those answers.
Yeah, of course. So all diamonds that come into GIA, if they're pink hued, they're going to be treated extremely carefully. So we are going to stabilize their color before doing any type of color grading. So that's using either a combination of strong white light or the 465 nanometer LED. And then we're going to ensure that the stone isn't subjected to UV light, or if it is subjected to UV light, we again stabilize it back to its stable color. So for instance, pink diamonds are stones that whenever they come into GIA, we do keep them for more than one day, just because we want to make sure that the stone has been graded correctly at the stable color and that they leave GIA at the stable color.
Okay. I have another question. It's to both of you. Can you permanently change the color of any diamond with shortwave or with ultra shortwave UV?
Not to my knowledge.
Not permanently. I mean, some of these color changes that we reported, you can certainly maintain the color change for an extended period of time. So for instance, research has shown that for those pink diamonds, you could potentially keep this excited bleached state for the order of 100 days, as long as you keep it in the dark. So you can keep it for a very long period of time, but eventually it will revert to its stable state.
Then I think I have one last question to Mike. Is there a specific part of the world that produces most chameleon diamonds? Are we aware of any geographic specificity?
I am not. It's always been something I've been interested in knowing, but given the difficulty in provenance origin information on diamond and the fact that the majority of diamonds are seen are faceted already, particularly chameleons, we don't. No, I'm sorry.
Okay. All right. Well, great. I think that's about it. I think we'll wrap up the questions. If you have any lingering questions, please find us on Instagram, Facebook, LinkedIn, and Twitter. Thank you all for coming and joining us. And again, next week, we'll be joined by Nathan Renfro and Dr. Aaron Pelkey, who will be discussing microfeatures of gems and their geologic implications. And thank you once again to Ulrika and Mike for your excellent presentation. Bye.